Welcome. You must be the student that's joining us. You've arrived at an interesting time. We've been looking into a strange new variant of dementia and have been dealing with some unexplainable types of findings. Patients behaving in ways that no one has seen before that can be difficult to watch. Okay, let's get you up to date with how we study dementia in this lab. Dementia is a gradual breakdown of memory, thought, and behavior. It's a condition with many variants that can be caused by different factors. And right now, this new variant is spreading in the brain in very unpredictable ways. What we do is discover equations that predict how dementia works in the mind, such as how fast does it spread and where. Then, we can find the factors that stop the spreading. We need to understand what's causing this anomalous variant to be so unnerving. So, how do we find these equations? Let's work this out together on a blackboard. We start by making a map of how brain regions are connected to each other by white matter pathways. This map is called a connectome. Each region is a cluster of neurons that together serve a distinct functional role. For instance, we can define one region as the hippocampus, which is important for memory formation. Normally, there are proteins called tau proteins that are responsible for maintaining the structure of neurons. However, due to reasons such as broken protein repair systems, tau proteins can become misfolded and damage white matter pathways instead of fixing them. It's been found that in dementia, there's a vast amount of misfolded tau proteins which spread throughout the brain. So, to understand how the brain's connections are affected under dementia, we need to measure how connected it remains before and after the condition progresses. This measurement will tell us how dementia distorts graph structure, helping us diagnose different types of dementia. For our new variant, we're seeing a yet unexplainable pattern of spreading and broken connections. Our current ways of measuring these patterns don't give us enough information to figure out what's causing the breakdowns. We need a new model. Take a look at this brain connectivity data. We need to find equations such that when we plug this data into them, we get values that explain important properties of this new variant. How do we do this? My best guess is that we should start by seeing how to modify equations that use a Graph Laplacian matrix. This equation is a simple form of what we currently use to model the tau spreading dynamics. I believe there's something we can do with its eigenvectors of the Graph Laplacian matrix, something to do with its spectral properties that will help us. I assume you've taken a glance at the data and medical reports before you got here. So, any ideas you have on how to modify this for our new variant? Your background report says that you were quite good in your linear algebra class, so if you stare at us long enough, I trust that you'll figure something out. Think of it as a rite of passage for every new researcher. If we don't throw you in the wilds, you'll never learn how to survive by yourself. I'll give you some more time. Though, frankly, we don't have much left. Cases of this new variant are rising faster with every passing day. I expect an update from you tomorrow. I just received a message. Hold on for a moment. So, a colleague of mine just reached out and expressed interest in helping out with our project. She's been a math professor at this university for a very long time. An incredible teacher, too. Though, she has been on leave for quite a while, for reasons that are unclear. Nonetheless, since she's an expert on our line of work, I believe she'll give us some very useful insights into solving this problem. Perhaps she could even give us the solution itself. She'll be joining us through a remote call. I'll introduce you to her. Hello, Evelyn. Glad you could join us. This is our new student researcher who's helping us with our work. As you've heard, we're discussing a strange new anomaly, and we believe the key to modeling it lies with the spectrum of the Graph Laplacian. We're lucky to have an expert on this subject here. Since we're looking to expand on this Graph Laplacian model, I think it's best if you give a recap of the Graph Laplacian matrix, and we'll use that definition in our derivation of the solution. Right. And we need to find its eigenvectors. Right. I'm sure your students had much to say about them. Let's take a look again at our problem. I recall you solved a similar problem some time ago. Can you walk us through its solution? That's great. But unfortunately, I think we're all a bit lost. Can you just tell us what the Graph Laplacian is? Then let's start from the basics. First, let's model the brain's connectome as a graph, which consists of nodes that are connected by edges. The nodes are connectome areas, while the edges are structural or functional connections between them. In our case, we're modeling these connections as white matter pathways, which transmit signals, such that nodes with stronger pathways communicate better. Our goal here is to figure out how connected each region is to each other, and to summarize this connectedness as a number that we can use to determine how badly dementia has wrecked the brain's connectivity. How do we calculate this? By using a collection of numbers called the Graph Laplacian matrix, or Graph Laplacian operator. Each row in the matrix corresponds to a node, and so does each column. This is made up of just two terms, d minus a. D is the degree matrix, and for each node, it contains the degree of that node. That is, how many neighbors that node has. A is the adjacency matrix, such that for each pair of nodes, there's a 1 if there's an edge between them, and a 0 if there's no edge between them. The values for these matrices are based on real-world pathway data, measured by medical instruments. Finally, the Graph Laplacian is just L equals D minus A. That should be enough for us to start using L to come up with some new equations. What do you mean by that? Okay, so you want me to explain why L is defined as D minus A, and why that's useful for conductivity. I think we can answer that by applying L on a graph of values. Let f be a function that assigns a value to each node. We can view f as a vector, such that each value is a component in a vector. F can be values, like the amount of white matter in a region, or how much tau has accumulated in a region, while L captures a node's connectivity. Given that L is a matrix and F is a vector, we can perform matrix vector multiplication using L times F. This is simple. We just take each row of L and multiply each element in that row by its corresponding element in F. This outputs a value in the vector LF. Since L equals D minus A, let's rewrite LF as DF minus AF. Let's look at a single row, or node, of LF. We'll perform an operation for matrix multiplication on it. If we describe what this math represents, we see that in the first term, it's multiplying the value of a node with its own degree, and in the second term, it's subtracting the sum of its neighbors' values. The reason why we're multiplying the node by its degree is because we're replicating the node's value once for each of its edges, so we can compare edge by edge. The more similar a node is to the sum of its neighbors, the lower the value of LF is for that node. The less similar a node is, the higher this value. That's how we describe the similarity for a single node. What about summarizing how similar a graph's nodes are to each other overall? We can add up the differences for every component in LF, weighing each component's difference by its assigned value in F. Which means nodes with larger values more strongly influence this summarized value. This gives us a single number that captures the global similarity of a graph. Formally, we'll do this by multiplying F as a row by LF. Given that matrix multiplication multiplies rows by columns, we turned F into a row using an operation called transpose. If we rearrange FLF, we obtain the following equation that calculates square differences, so the sign doesn't matter. For the sake of time, let's not go into this derivation for now. This FLF value is what we call the smoothness of a graph. Smoothness is the overall similarity or variation across nodes in a graph. When nodes are more similar in value, the graph is smoother. And when they're more different, the graph is rougher. One reason why it's called this is because when you're feeling how smooth a surface is, you don't just put your finger on one point of it, but you brush your hands across the surface. We can use smoothness to tell the overall differences in graph structure between two graphs. Note that different values of f will give different types of smoothness, so smoothness is relative to each f. Now, we're finally getting to what's most important for its problem, the eigenvectors. They're defined as any vector v such that L times v equals lambda times v, where lambda is the eigenvalue of an eigenvector. If we find the eigenvectors, they'll tell us the most important properties of the graph. After all, they're its distinct modes of variation. The eigenvectors characterize the intrinsic properties of the graph through spectral embeddings. Sums of eigenvectors are solutions at time t to the diffusion equation that describes tau protein spreading dynamics. The solution, right? What do you remember? What do you mean by that? Why can't we just solve for the eigenvectors? What would happen? Evelyn, can I have a moment alone with our student? Keep this just between us. But I don't think Evelyn is who she used to be. I think we have to let her go. Evelyn, we've been talking about how we should proceed from now on, and we've come to a difficult decision. I think it might be better for you to take a rest and step away from research. Thank you for joining us today. Evelyn, you keep on saying that. What do you want to tell us? I'm sorry, Evelyn. Let's talk again soon, okay? It was wonderful meeting you today. I just received reports that the anomaly is spreading even faster. Let's work as quickly as we can. I'll talk to you tomorrow. What did you call me in for? Did you make progress on a new model yet? I know it's hard, but you have to let her go. How exactly? You're saying the whispers she's talking about are eigenvectors, and you don't think that's just a bunch of nonsense? Hold on. Now that I think about it, that actually makes a bit of sense now. You might be onto something. The more I think about this, the more it starts to make sense. You've sparked my curiosity. I'm still skeptical, but I'll give this meeting one more chance. Evelyn, I have something to ask you. Are the whispers eigenvectors? And so are the dyes, the X-ray dyes. Then the X-ray is the Laplacian. Sorry, that made me sound off, but I'm beginning to understand. Evelyn, do you want me to explain the eigenvectors again, but more intuitively? Okay then, let's pick off from where we left off. This time, I think I can talk about the eigenvectors with a bit more detail, and in a rather different way. Let's recap what problem we're trying to solve. Because a brain network's connectivity is damaged by misfolded tau proteins, the structure of L changes. So we want to compare graph connectivity structures before and after dementia. How do we measure how connected it is? There are several properties we can look at. For one, we don't want a brain to split into two, with no edges between the two clusters. We want it to still remain connected. But a weakly connected brain can be split by just removing a few of its connections, while a strongly connected brain would still be connected if we've removed those connections. Is it possible to summarize this property of a brain with just a single number? The answer is, remarkably, yes. How do we do this using L? Note that our Graph Laplacian operator can tell us how connected each node is to each of its neighbors. However, L has to be applied to a function on the nodes to have meaning, such as how LF allows you to calculate smoothness. If you just calculate d minus a, notice that for each row, the degree minus the sum of neighbors will always cancel out into 0. This is the same as multiplying L by a function that assigns the same value to every node. This is meaningless, so we need a function that doesn't just assign the same value to every node, but somehow can still capture the connectivities of a graph. What function should we choose? We should choose a function such that, after applying L on it, preserves the structure of the graph as purely as possible as we brush past it. In other words, instead of the output being 0 in every component in LF, we should capture the underlying difference between a node and its neighbors, such that F doesn't artificially amplify one region or another. For instance, F can be the amount of tau proteins in a region. One region may have a lot of proteins, while its few neighbors have little. So LF for tau would be high. But without those tau values, that region, having very few neighbors, would be a region that is vulnerable to being part of the bridge that splits the graph into two. if its connections were removed. You're probably still wondering what this has to do with either eigenvectors or X-ray dyes, but I'm getting there. What we need to do is define a function such that if we assign the right values to this region, it reveals that it's a vulnerable region, a weakly connected bridge between two clusters. Now, I'll describe what kind of function can do this. As an analogy, let's imagine we have a maze, but we can't see all of its tunnels. This is like how when we do X-ray imaging, in which we have to inject a dye into a body to illuminate its structures, like organs or blood vessels. The dye shouldn't expand or shrink any of these organs or blood vessels disproportionate to every other structure. It should only allow them to be captured by the X-ray. That means only certain dyes are suitable for X-rays. Assigning values using a function is analogous to using an X-ray dye, and L is the X-ray that measures the shape of the dye after it's poured into the body's tunnels. Thus, we need a good dye that allows us to measure the shape of these tunnels without any errors caused by our measuring tools, like the dye. Thus, the dyes that preserve the shape as best as possible are analogous to eigenvectors. When L is applied onto this function, an eigenvector, the output values in LF should scale proportionally the same way for every node. The output is just a scaled copy of the original, with no distortions to its connectivities. It sounds like a stretch, but if you really follow this from the assumption that the X-ray dyes are analogous to eigenvectors, the rest of these connections just naturally come through. Evelyn, does this sound like what you were trying to tell us? Shadows of the graph. I see. I'm starting to understand where this is going. Evelyn, what do you think the Laplacian is when we talk about shadows of the graph? Then the eigenvectors in this case. If the shadows scale perfectly if you point them at the graph in a certain way, the eigenvectors must be certain angles you tilt your flashlight to. I get it now. It makes sense. When we shine a flashlight on an object, it creates a shadow on a wall. If we shine the flashlight at certain angles, this shadow is distorted. If you try it yourself, you almost don't notice these distortions as they're subtle, but they're there. As we rotate the flashlight, the shadow even changes shape. But there are certain angles where the shadow will scale proportional to the original object. Now, imagine this object is our graph, and the flashlight is our Graph Laplacian operator. The angle is our function f. LF is a shadow on the wall. And those certain angles that make the shadow look like a scale proportionally to our graph are our eigenvectors. How much the flashlight scales the object is our eigenvalue. Now, the shadow is merely a 2D projection of the original 3D object. It's more accurate to say that LF is a scaled copy of a 2D projection of the object from a certain angle, or, in other words, a scaled copy of the eigenvector of the graph, rather than the entire graph itself. So, different shadows will give you different properties of the original object. Analogously, different eigenvectors will tell us different properties of the graph. Different eigenvectors have different eigenvalues, which we can order from small to large. So, we can distinguish different eigenvectors by the ranking of their eigenvalue relative to others. Across two graphs, we can compare their eigenvalues of their ranked eigenvectors to assess if one graph is more connected than the other. There's still two more mysteries that linger, the bell and the whispers. I have an idea what they are, but a few connections are still missing. Evelyn, can you tell us about how you taught your classes? They said you were an incredible teacher. I see. So we need to connect these analogies back to our mathematical definitions. Okay then, let's call an eigenvector v. So recall that LV equals lambda times v, where lambdas are eigenvalue. Now, what does it mean for the same graph when one of its eigenvectors has a larger eigenvalue than another one of its eigenvectors? Given the meaning of what LF is measuring, LV means the difference between node I and its neighbors is proportional to node I. But this eigenvalue, or proportionality, is the same for every node. It's not just for one node. It's a global measurement. Thus, when an eigenvalue is small, while individual nodes can still have large local differences with their neighbors, these differences as a whole are not as large in comparison to when this eigenvalue is large. That means lower ranked eigenvectors have smoother patterns than higher ranked eigenvectors. Recall that different values of f will give different types of smoothness. So smoothness is relative to the f you choose for the graph. However, the f we use here are eigenvectors, and each eigenvector captures an inherent property of the graph, such as its connectivity. That means when we're talking about the smoothness of a certain eigenvector, we're also linking how smoothness correlates with a certain graph connectivity property, and we can use a Graph Laplacian smoothness measure on eigenvectors to compare different graphs. We just explained how we interpret eigenvectors, and following what I think Evelyn would say, I know just what we need to do next. Let's go over the intuition behind a few of these ranked eigenvectors. We'll start with the first one, the lowest eigenvector, which assigns the same value to every node. This is the smoothest the graph can be, but it doesn't say anything meaningful about the graph structure, because there are no differences between nodes. So for all graphs, its eigenvalue is always 0, and we can't use this to compare graphs. So let's look at the second lowest eigenvalue. Because L gives the difference between a node and the sum of its neighbors, and we want the lowest eigenvalue we can get from this graph through node value assignment, we want an assignment which tries to minimize this difference as much as possible without assigning the same value to every node. Not only that, this assignment requires that LV is proportional to V. This is an interesting puzzle, so let's look at an example where we try to minimize the smoothness as much as possible. First, we'll try to do this without the constraint that LV must be proportional to V. We'll start with a graph that has one cluster of nodes, 1, 2, and 3, all fully connected to each other, and it has another cluster of nodes, 4, 5, and 6, also fully connected. Lastly, it has one bridge edge between the two clusters, between nodes 3 and 4. We started by assigning every node the same value, but now we need to give at least one node a different value. Let's give node 4 the value 0.5. The total smoothness is now 0.75. This is because node 4 now has differences with 3 nodes, nodes 3, 5, and 6, and each difference has a squared value of 0.5 squared, or 0.25. Can we improve the smoothness? Let's first try this assignment, where we make node 3 the same value as node 4. This tries to minimize the smoothness of the bridge, but the total smoothness is 1, since each cluster has smoothness 0.5. while the bridge has smoothness 0. The total smoothness of 1 is worse than the previous smoothness of 0.75. What did we do wrong? Notice that before, node 4 had differences with 3 nodes. So we should instead try to make it be similar to nodes 5 and 6 within its own cluster, rather than be similar to the node it's part of a bridge with. So we can do even better. Let's try this assignment, where we assign the same value in each cluster. If we calculate the smoothness now, both clusters have 0 smoothness, while the bridge has smoothness 0.25. The total smoothness is 0.25. Why was this assignment better than the others? Because the clusters have more edges than the bridges. Thus, we want to put the differences in the bridges as much as possible. Why can't we just count the number of edges in bridges? In our simple example, we can, but graphs can consist of billions of edges, with structures so complex that it's not easy to find and identify every possible combination of edges that can disconnect them. However, by solving for eigenvalues, we can describe graph connectivity properties simply and efficiently. Now, our assignment was not an eigenvector, but we can solve for the eigenvector using certain algorithms and obtain the actual second smallest eigenvector for the graph, which has an eigenvalue of 0.438. Notice that the first cluster has all negative values close to each other, while the second cluster has all positive values. The bridge has the biggest difference, with a positive value that's highly different from a negative value. So, what graph property is this eigenvector capturing? Let's go back to our vector that assigns the 1 and 0.5 values, and look at a variation of this example by adding one more edge to the bridge. This increases the total differences in the bridge and increases the smoothness to 0.5. In other words, the graph is rougher along this vector and is harder to split by the bridge because there are more edges in the bridge. Its eigenvalue also increases. The new eigenvector has an eigenvalue of 0.764, which increased from the more disconnected graph's eigenvalue of 0.438. With this new graph, this is the best assignment that can be done to try to minimize smoothness as best as possible without assigning the same value to every node. As a distinct minimum, it shows that no matter what, you can't get this more connected graph to be as smooth as the less connected graph along this eigenvector. This is because the bridges in this graph are too strong to break and can't be made as smooth as they can, like in the less connected graph. In general, the second smallest eigenvector is called the Fiedler vector, and its eigenvalue is called the Fiedler value, which allows us to compare how easy it is to split a graph into two disconnected components using a single value. Typically, a brain with dementia would be more disconnected because its white matter pathways degrade, and thus would have a smaller Fiedler value. When a bridge is easier to break, that means there's not as many backup edges to help save it. Note that we're not actually saying that dementia splits a brain into two. Think of the Fiedler value just as a hypothetical litmus test. If we were to try to do so, we can use how easy it is to split a brain to diagnose dementia. The smoothness of an eigenvector is like a medical test, and we can use the Fiedler value like a biomarker. Now, what properties do higher order eigenvectors capture? They assign different patterns of smoothness, so each one progressively reveals more detailed patterns or variations. In dementia, since connectomes become smoother, many of their eigenvalues tend to become lower too. Therefore, if you look at a list of eigenvalues, called a spectrum, we see that brains with dementia tend to have lower values in their spectrum. Instead of just comparing a single eigenvalue to another, we can compare entire spectra of eigenvalues and obtain even more information about the two graphs. Now, we want to predict how tau spreads. We'll still calculate the Laplacian using white matter connectivities, but instead of applying it on the eigenvectors of the white matter graph, we'll apply it to a new function, the tau protein concentrations. We use this to obtain the diffusion equation of tau proteins. Here, we're not just getting the structure of the brain's connections, which set the stage for possible spreading patterns, but we're predicting how tau diffuses along those connections as time goes on. How do we get this equation? We'll start by describing the rate of change in the concentration of tau at a single node over time t. Imagine a graph of just two nodes. Based on real-world observations, we assume that the amount of substance that moves from node A to node B over a time period dt is proportional to Fa minus Fb. So we can write that the rate of change for F at node I is equal to their difference times C, where C is a constant describing the diffusion strength. Now, if this node had more neighbors, its rate of change would be the sum of its neighbors' differences. Does this sound familiar to how the Laplacian captures the difference between a node and the sum of its neighbors? If we derive the rate of change of f for the entire graph, where f is a vector, we get that it's equal to negative c times L times f. We won't have time to derive it, but let's get some intuition on how to interpret it. In diffusion, higher concentrations want to spread to lower concentrations until everything balances out. A high F value means it wants the concentration to go down. So negative CLF describes how it'll change. But this differential equation doesn't state the exact amount of tau at node I during time t. This value is represented by f of t. But we can use this differential equation to solve for f. So what's the equation for f of t? Again, we won't derive it. We'll only get a high-level intuition. Note that the rate of change of f is proportional to itself after applying L. This also sounds familiar, like the eigenvectors. Though our f is not an eigenvector, this similarity is intuitively connected to how, if you were to derive f, you would see that it's a sum of eigenvectors. So is f of t just equal to the sum of eigenvectors? Not quite. At time t equals 0, where we just apply L once to f, you can just write f of 0 as just a sum of eigenvectors, each scaled by a weight alpha that tells us how much each eigenvector contributes to the total sum. But f of t describes concentration at different stages of t, which means we apply L continuously over time. Each tiny step in time, or delta t, shifts f over and over again, proportional to the time step before, which grows bigger than before. If we substitute in the f from a previous time step, we see that each time step adds another power of L, colloquially speaking. This compounding evolution is captured by the exponential function. Expanding e will reveal that it's like the sum of applying L once, applying L twice, and so forth. If you were to derive one term of f of t, you'd find that you must multiply the initial concentrations, f of 0, by the exponential function raised to the power of negative c times an eigenvalue times t, and finally multiply all of this by an eigenvector. Finally, f of t is a sum of multiple of these eigenvector-infused terms. Note that the initial concentration is multiplied by each eigenvector to produce a scalar weight that denotes how much that eigenvector contributes to the initial concentration. Another intuitive concept is this. The rate of change of f is proportional to itself, and a derivative of the exponential is also itself. But what does this all mean? Recall that each eigenvector gives graph structure properties, so if we take them in combination, they act as an alphabet that builds up a language describing how tau spreads along the graph structure. What's more, each eigenvector term is independent from each other, meaning they scale at their own rate. Given that we multiply t by -1, as t gets larger, the exponential in this eigenvector-infused term grows smaller. So we can say that each eigenvector term is decaying at its own rate. But what's more, the terms with higher eigenvalues will decay faster than terms with lower eigenvalues. The eigenvalues control the rate of decay. Therefore, as we approach the end of time, only the lowest eigenvectors remain. How can all these eigenvectors exist at the same time if f only assigns one value per node? Evelyn, I believe this is starting to sound more familiar to you. Just as I guessed. When you first strike a bell, you hear a very complex and noisy sound, as it's vibrating in many different frequencies at once. But over time, the sharper, higher-pitched parts fade away, and what remains is just a low, smooth hum that lingers. The eigenvalues are like frequencies, and over time, the higher eigenvectors fade, leaving only the low, droning hum of the lower eigenvectors. This is also like how a song starts off with many instruments playing together with variations and notes, but over time, only monotonous static, with slow, steady echoes, remains. There is one more connection to make here. The exponential decay equation, which models many decaying phenomena, such as radioactive decay, is usually written with the following symbols. Does this ring a bell? This is just the diffusion equation if it were to be expressed with one eigenvector. So we can say that the diffusion equation is the weighted sum of many exponential decays, one for each eigenvector. However, notice that instead of writing the eigenvalue, we have this strange term here. What is it? This term is analogous to our eigenvalue. This symbol right below is what we call tau, the time decay constant. That means for our case, the inverse eigenvalues of our mind are tau, and they tell us where the tau proteins end up in our mind. Yet, in the end, tau is not tau. Don't mix them up. Keep them distinct in memory. I think this is a good place to stop. What do you think is missing? That was beautiful. We're very grateful to have talked to you today. Thank you. You've helped us so much. Take care, Evelyn. And goodbye. We didn't find a solution to our problem yet, but no worries. These things take time. What's important is that you learn something meaningful. And I suppose you're not the only one who did. Let's continue to work on this problem later. Tomorrow, I'll spend a little more time walking you through our research, and you can take a week to look for patterns in this new data I'll send you. Don't hesitate to come to me if you have any questions. But before you go, just one more thing to keep in mind. Every once in a while, remember to check in on your connections. We shouldn't let each other drift apart. I'll see you tomorrow.